In this video, we're going to look at a specific kind of discrete dynamical system that leads to what are known as Markov chains. Discrete dynamical systems often describe situations where objects move between different states. We saw that in the previous video. Another example, let's say we have a social media platform and we are keeping track of whether our users are active or inactive. So A for active, I for inactive. Let's say each month we know that 85% of active users remain active, 15% of active users become inactive, and then 40% of inactive users become active again, 60% of inactive users remain inactive. We might have our state vector xk, which consists of the active users as the first component and the inactive as the second component. So if we were looking for our matrix A, so that xk plus 1 equals axk, we saw earlier sort of how we might approach this, where we really want to know what happens to just a few special vectors. But in the last video, this led to a matrix similar to what we're going to see here, where we'd have the first column being those percentages written as decimals for what would happen to our active users, and then the second column being the percentages for our inactive users. And then we can use this matrix to compute, kind of what's going to happen as we progress. So suppose we begin with x0 is 1, 0, then x1 would be ax0, which would be 0.85, 0.15, 0.4.6 times 1, 0. And so this would be exactly 0.85, 0.15. Now, the vector 1, 0 here is probably not talking about a platform where we have, just one user total, and that one user is active, but instead it's talking about percentages. So that 1, 0 is basically saying 100% of the users are active. And so after one step here, one iteration, we would end up with this vector where now 85% of our users are active and 15% are inactive. And then we could find x2, saw in a previous video that this is a squared times x0. And so we could compute that and figure out, sort of where we are after two steps. And so do that computation here. And you can use other technology. You can do it by hand, certainly. But if you have some technology available to do some matrix powers, some matrix multiplication, that definitely simplifies things. And then you can look at more and more powers as you go. So just putting this into my calculator here, let's go through the math. Okay, and this is going to round this here to about 0.75, 0.25. And so after 2 months, 75% of the users would be active, 25 inactive. We can then look at 3 months. So this would be x3. This is going to be a cubed times x0. And so that is about 0.74, 0.26. These are approximations, but rounded to 2 decimal places there. Okay, so we can see after 3 months, if all of our users began as active, after 3 months, we would have this distribution. So when we talk about Markov chains, the future state of the system depends only on the current state. It does not depend on how the system arrived at that state. So, for our social media example, if we want to know how many users are active or inactive after k plus 1 steps, we only need to look at that previous month. We don't need to look at sort of a larger distribution of months or anything, before that previous month. This type of discrete dynamical system is called a Markov chain. And we're going to more specifically define Markov chain a little bit later in this video. Sometimes our vectors represent probabilities instead of counts. We saw that with that example earlier. So x would be 0.85.15 represents an 85% chance of being active, 15% chance of being inactive. So this could be probabilities or percentage of users. So a vector whose entries are non-negative and add to 1 is called a probability vector, and a square matrix, that is an n by n matrix, whose columns are probability vectors, is called a stochastic matrix. And if we go back to our matrix here that we defined for that social media example, this is a stochastic matrix. You can add up each of the columns, right, and they each add to 1. Which, if you think about how we actually derived this matrix, that makes a lot of sense. So now for a more specific definition here of a Markov chain, suppose we have a stochastic matrix, A. So all of the columns of A, the values in each of those columns add to 1, and a probability vector x0. If we form the sequence of vectors x0, x1, x2, and so on, where xk plus 1 equals a times xk, then this sequence is what's known as a Markov chain. So let's do another example here. We're going to try a 3x3 example. So suppose education level is divided into 3 groups. We'll say C is completed college, H is completed high school only, and N is did not complete high school. We study how education levels change from generation to the next. So suppose the transmission matrix is given by this matrix here. So just like, for example, taking this first column, this 0.7, 0.2, 0.1, so that first column is going to be representing the, transitions from the completed college group to the other groups. So this tells me that if someone completes college, then their children, the next generation, have a 70% chance of completing college, a 20% chance of completing high school only, and a 10% chance of completing neither, not completing high school, right? And so this is the generation after C, after completing college. This second column is the generation after H. So if someone just completed high school but not college, there's a 50% chance the next generation would complete college, 30% they would just complete high school, 20% that they would not complete high school. And these are, I should point out, just completely made up probabilities for this example. This would be, I think, an interesting example to actually look up some data on and try and construct. I'm sure that there is some relationship, of course, between these, generation to generation, how much education, but just for the sake of this example, these are all made up. And we could go through that third column as well. So that the columns again describe the probabilities for the next generation. So suppose the current generation has this distribution. So 30% complete college, 50% high school, 20% not high school. Find the distribution of the next generation. And so we would take our matrix A, given here, and multiply it by x0. So A, x0, if we put that in our calculator, we would find that that distribution would be 0.52, 0.29, 0.19. And then we could keep going. So x2 would be ax1 or a squared x0. And if we put that in our calculator, we would get about 0.566, 0.267, and 0.167. I do encourage you to try this out in your calculator. If you want to do it by hand, you certainly are welcome, but your calculator is probably fine. If we wanted to go to the next generation, x3, that would be ax2 or a cubed x0, and that would be, start rounding here, approximately, say, 0.58, and then 0.26, and then 0.16, and these are just approximations at this point. What happens after many generations? So we could, keep going or use our calculator to find higher powers of this matrix. We could see, for example, x20, so 20 generations later would be a to the 20th x0, and that would be 0.586, 0.257, 0.157. So 20 generations later, we'd have about, a little more than 58% completing college, 26%, around 26% completing high school, and about 16% completing, not completing high school. One thing that's kind of interesting is if we were to go even further into the future, let's say we wanted to go 100 generations later, this would be a to the 100th x0. I certainly don't recommend you do this by hand, but again, if you have some technology, you can plug this in. You would find that actually the result would be exactly the same as, if we're doing some rounding, but close enough, exactly the same as the a to the 20th. So we are kind of seemingly honing in on some particular distribution of the number of or the percentage of our population that is getting certain education levels. These values, these 0.586, 0.257, 0.157, are related, of course, to this matrix A. How they are related is something we're going to see in a later chapter. But for now, just recognize that if we take this power high enough, then we will eventually get sort of this honing in on this particular matrix. We call this a steady state result here. And it actually will not even depend on the initial vector x0 that we plug in, which is interesting. So again, these are all things we're going to be seeing later on in the course.